120 light-years from Earth, deep in the constellation Leo, a telescope has captured something truly profound. It's a discovery that promises to rewrite everything we thought we knew about life in the universe. The James Webb Space Telescope detected a world, shrouded in an atmosphere, where the temperature remains a steady 49 degrees Celsius. It pulses with the unmistakable chemical signature of living creatures. Scientists are not just hopeful, they are 99.7% certain. This isn't just a planet, it's a world teeming with life, perhaps even more habitable than Earth itself. The numbers arrived on a Tuesday morning in December, tucked away within streams of light, gathered by the James Webb. At Cambridge University, astrophysicist Niku Medusan stared at his screen. He watched the faint dips and rises of light, signals that had traveled more than a century across the vastness of interstellar space. Every curve was a clue, a hidden story etched in photons. Then came the anomaly. A single molecule that simply shouldn't have been there, dimethyl sulfide. On Earth, this specific molecule is produced exclusively by life. It comes from plankton in our oceans, from bacteria in our soil, from the metabolism of countless unseen organisms. It doesn't form from volcanoes, or lightning, or mineral reactions. Only biology makes it. And the signal wasn't faint. The probability of error was less than 3 in 1,000. Medusan's hands trembled, not from cold, but from sheer, overwhelming excitement. Somewhere, 120 light-years away, something alive was undeniably showing itself in the cosmic void. The world producing this extraordinary signal is named K2-18b. It orbits a small, steady red dwarf star, nestled within the constellation Leo. This planet is roughly 8 times the mass of Earth, large enough to hold onto a deep, dense atmosphere, yet small enough to avoid becoming a gas giant. For years, astronomers had assumed such worlds were too hostile for life. Their thick hydrogen blankets, their crushing gravity, it all seemed utterly unwelcoming. But Webb's data painted a different picture. Beneath that dense, hydrogen-rich atmosphere, the temperature holds steady, at around 49 degrees Celsius. This is warm, yes, but gentle enough for vast quantities of liquid water. The hydrogen itself acts as a perfect insulator, trapping heat and redistributing it evenly across the entire globe. Medusan's team had been studying K2-18b for months, meticulously capturing the faint starlight that filtered through its atmosphere each time it transited in front of its parent star. Each transit revealed more. First, water vapor. Then methane. Then carbon dioxide. A cocktail of gases that, together, painted a picture of remarkable balance and stabilization. And then, finally, came the dimethyl sulfide, the unmistakable scent of life. In the realm of astronomy, absolute certainty is incredibly rare. Most discoveries begin as whispers of possibility, easily overturned by later, more refined data. But this one carried 99.7% confidence. This level of statistical strength is usually reserved for monumental discoveries like subatomic particles or gravitational waves. For the first time in human history, we weren't just guessing about life beyond Earth. We were almost sure. The planet's thick atmosphere acts like a planetary greenhouse, but not a hostile one. Instead of trapping destructive, runaway heat, it creates a perfect thermal equilibrium. Water there neither freezes nor boils. It simply exists, vast, deep, and incredibly stable. Such a world would be a paradise for chemistry. Life would not need to constantly fight against droughts or harsh winters. Evolution could unfold continuously, like a beautiful, unending melody. Its parent star burns faintly compared to our sun. It's small, steady, and remarkably long-lived, almost immortal. Red dwarfs can live for trillions of years. Their flames are soft, but they are eternal. Around such stars, time itself becomes a generous, boundless commodity. Any spark of biology that begins there might have ages beyond our imagination to grow, to adapt, to transform itself. When the initial results were announced, the scientific world simply paused. For decades, we had searched tirelessly for Earth's twin, a rocky planet orbiting a yellow sun, just like ours. Yet here was something entirely different, and somehow, even better suited to life. It wasn't merely similar to Earth. It was a completely new category of habitable world. Imagine vast oceans beneath alien skies, life sustained not by resemblance to us, but by the sheer, boundless creativity of the universe itself. To see such a world, Webb had to perform miracles of engineering and observation. Suspended 1,000,000 miles from home, at a gravitational point known as L2, the telescope lives in permanent darkness. Its 5-layered sun shield, the size of a tennis court, keeps it colder than the surface of Pluto. 18 golden mirrors, each a hexagon of perfect geometry, collect light invisible to our human eyes. Together, they create a mirror so precise it could theoretically detect the warmth of a bumblebee on the moon. When that distant planet drifts in front of its star, a tiny fraction of the star's light filters through K2-18b's atmosphere. Molecules suspended in that air absorb specific wavelengths, leaving faint, unique imprints, a spectral fingerprint. By decoding those intricate patterns, Webb reveals the planet's precise chemistry. It's like identifying a voice simply by analyzing its breath. But detecting that whisper is unimaginably difficult. The host star itself shines billions of times brighter than its tiny planet. To overcome this overwhelming glare, Webb employs its coronagraph, a special mask that blocks the star's blinding light, much like holding your thumb over the sun to spot a firefly nearby. The remaining starlight is then carefully filtered, analyzed, and stripped of noise by algorithms so precise they can separate a handful of meaningful photons from millions of empty ones. Those photons carry stories older than memory. Each one left its home world 120 years ago, around the same time humans first learned to send radio waves into our own sky. Now, a century later, it tells us that life was already thriving elsewhere. It's humbling to realize we're not discovering life as it begins, but as it was, a century-old echo of a living planet that has likely continued its vibrant existence ever since. The atmosphere of K2-18b revealed even more than just chemistry. It revealed behavior. Methane, carbon dioxide, and water vapor formed a delicate balance, a kind of planetary metabolism. On a lifeless world, such gases would quickly react and settle into a state of chemical equilibrium. But equilibrium wasn't what Webb observed. Instead, the ratios fluctuated. This was a state of chemical disequilibrium, precisely the same signature that defines Earth's living air. Life doesn't allow for perfect, static balance. It constantly reshapes its environment, breathing, consuming, exhaling. Even the planet's missing gases told a story. If K2-18b were lifeless, its skies would almost certainly be filled with ammonia. But ammonia was almost entirely absent, as though something were actively using it, converting it, effectively cleaning the air. On Earth, microbes do exactly that. The deeper the analysis went, the clearer the picture became. Not a sterile world, but a thriving one. Not a fluke of chemistry, but an ecosystem on a planetary scale. Statistically, the confidence was overwhelming, a 3 sigma detection, 99.7% certainty, meaning the chance of error was roughly 1 in 1,000. In any other scientific field, that level of evidence is beyond question. And yet, no number could truly capture the enormity of what it implied. For centuries, we had asked whether life existed elsewhere. Now, for the very first time, the answer was not mere speculation. It was measurement. To reach that conclusion, Webb had to detect molecular patterns only a few parts per billion in strength. This is the spectral equivalent of hearing a faint heartbeat through the roar of a hurricane. Light was measured to 1 part in 10 million. Each wavelength recorded and meticulously compared, every alternative explanation systematically ruled out. Contamination from Earth was impossible. Random noise was statistically negligible. The simplest explanation, in fact, the only explanation, was biology. That's why the moment the data was confirmed, every scientist who saw it felt the same quiet, profound weight. This wasn't just another exoplanet. It was the end of cosmic solitude. The planet's vast oceans, perhaps hundreds of miles deep, blur the very line between sea and sky. The water mixes with hydrogen, creating a liquid that remains stable across a staggering range of temperatures. Such unique chemistry could nurture life forms beyond our wildest imagination. Creatures that might breathe hydrogen instead of oxygen, feeding on methane instead of sunlight. Under its perpetual clouds, pressure builds into conditions we can barely simulate on Earth. Diamonds may even form and rain through the atmosphere, glittering down into the oceans like frozen stars. Somewhere below that luminous haze, in the warm, twilight waters, life is almost certainly stirring. Not fragile, not temporary, but ancient and abundant. This realization changes everything. If biology can thrive in hydrogen seas around a red dwarf star, then life isn't rare at all. It's inevitable. 3/4 of the stars in our galaxy are red dwarfs, quiet, enduring suns with planets just like K2-18b. If even a fraction of them host biospheres, then our Milky Way galaxy is overflowing with living worlds. The discovery redefines what habitable truly means. It tells us that life doesn't necessarily need an Earth clone. It only needs balance. The right chemistry, the right temperature, and the right patience. Webb's golden mirrors did more than just observe. They connected us to another chapter of creation. Each photon it caught carried a whisper across space and time. The breath of an unseen ocean. The sigh of life beyond our reach. In that faint light, humanity found proof that existence is shared, that we are not the first, not the only, and certainly not the last. The universe, it seems, has been alive for more time than we can logically imagine. The red dwarf at the heart of this system is small enough to fit inside Jupiter, yet incredibly dense. Its gravity is powerful enough to hold a planet like K2-18b in its embrace for eternity. Its light is dim, a deep ember red rather than the fierce white blaze of our sun. To human eyes, it would not dazzle, it would merely glow, soft, constant, patient. This is not a star that lives fast and dies young. It burns slowly, almost tenderly, stretching its lifetime not into billions, but into trillions of years. In the vast scale of the cosmos, it is nearly immortal. That astonishing longevity changes everything for K2-18b. Around our own sun, light shifts, climates wobble, and extinction events follow one after another. But here, the light remains steady. The same warmth, century after century, millennium after millennium. No wild flares to strip away an atmosphere. No sudden chaos to undo the intricate work of chemistry. For a world like K2-18b, that profound constancy means something extraordinary. Oceans that never freeze. Clouds that never vanish. And time, endless time, for life to rise, adapt, and endure without interruption. For decades, scientists largely dismissed red dwarfs as unfit for life. They are small, they are cool, and their habitable zones lie so incredibly close that any planet must orbit almost hugging the star. What once looked like a dangerous, volatile proximity, however, turns out to be remarkably ideal. K2-18b completes a year in just 33 Earth days. It's close enough to feel the persistent warmth of its dim sun, yet far enough to remain calm and stable. One side always faces the daylight, locked in an eternal afternoon. The other sleeps in perpetual darkness. From space, it would appear like a glowing marble, half bathed in crimson light, half wrapped in impenetrable shadow. Yet, even that night side is not truly cold. The planet's thick hydrogen atmosphere acts as a vast, efficient conveyor of heat, tirelessly moving energy across its immense skies. That kind of global stability is exceptionally rare in the universe. It gives water a permanence, allows weather to flow without violence, and provides chemistry with a profound peace. If life exists there, it evolves beneath a sun that never truly rises and never truly sets. It is a world caught in an eternal twilight, where the line dividing day from night is not a stark frontier, but a vast, continuous habitat. Under that perpetual twilight, the color of the sky would never be blue. It would burn in layers of crimson, violet, and copper, dim, yes, but endless. The star itself would hang motionless above the horizon, fixed in the same spot forever. The oceans below would reflect that deep red light, glowing faintly as waves move under a horizon blurred by haze. On the night side, darkness would not be absolute. The dense air would scatter the star's glow, painting the blackness in faint, metallic hues. Even there, light would linger, the glow of auroras, the shimmer of lightning inside distant clouds. This is not a planet of stark contrasts, but of gradients. One where everything shifts smoothly, never abruptly. If evolution began here, it did so with patience. On Earth, life was shaped by disaster, impacts, ice ages, and sudden bursts of fire. But around this quiet sun, there are no mass extinctions, no sudden, cataclysmic ends. The rhythm of time is slower, the canvas broader. Life here could grow old without interruption, carried forward on the calm, steady breath of a red dwarf dawn. Webb's instruments were born to see in this particular kind of light, infrared, the very wavelength red dwarfs emit most strongly. That is precisely what made K2-18b's signature so clear and undeniable. The telescope wasn't straining to see something faint. It was perfectly tuned to the exact language of the star itself. Every beam of infrared light carried within it the intricate code of the planet's atmosphere, the heat of its clouds, the subtle scent of its oceans, the very breath of unseen organisms. Each time the planet crossed the face of its star, a tiny fraction of starlight slipped through its air. Molecules within that atmosphere absorbed specific wavelengths of that light, leaving faint, characteristic notches, spectral fingerprints. Webb read them like a diary written in light. The pages spoke of water, methane, carbon dioxide, and then, finally, dimethyl sulfide, the unmistakable mark of life. To human eyes, the red dwarf itself would appear unremarkable, barely visible in the night sky. Yet, that very dimness makes this discovery possible. The smaller the star, the easier it is to see its planets. The glare is reduced. The signals are cleaner. What seems weak is, in truth, perfect. Red dwarfs are not obstacles. They are cosmic magnifying glasses, revealing the faint whispers of their worlds. If we could stand on one of K2-18b's high plateaus and look up, the view would be truly surreal. The horizon would curve beneath a bronze sky. The air would shimmer with heat. The sunlight would feel soft, more like warmth than brightness. Shadows would be long and lazy, stretching into infinity. The very concept of day and night would fade, replaced by slow, gentle shifts in tone, in temperature, in the heartbeat of the planet itself. Life, if it exists there, would move differently. Plants might be dark, black, indigo, or deep violet, absorbing every stray photon of red light. Photosynthesis would be slow but steady. The creatures that graze on them might sense the world through vibration or pressure rather than sight. Nothing would hurry. Energy is scarce, but time is infinite. Evolution would reward patience over speed, endurance over aggression. The red dwarf's greatest gift is moderation. It burns with discipline, never wasting, never surging. While our sun will expand and die within 5 billion years, K2-18b's parent star will still be glowing softly when the Milky Way has changed beyond recognition. For the life orbiting it, apocalypse is a word without meaning. When Webb's instruments detected light from K2-18b, that light had been traveling for 120 years. When it began its journey, the year on Earth was 1905. Einstein was writing about relativity. The Wright brothers were testing powered flight. Our species had barely learned to reach the sky, while that distant planet had already been breathing beneath one for eons. It means that what we see is not the present, but the past. A memory of a living world as it was a century ago. And when we look again decades from now, we will still be catching up to that moment. Astronomy is always a conversation across time, and the universe speaks slowly. Yet even a whisper from 120 light-years away can rewrite everything we believe. The chemistry in that air, the unique mixture of gases, the essential imbalance that only life can maintain, dances to the steady beat of its star. The red dwarf provides a constant rhythm. The planet answers with metabolism. Together, they form a perfect loop, one stable, one alive. It is a relationship of opposites, a duet between fire and breath. The star gives constancy. The planet gives change. One burns, the other renews. Our own world began in chaos, fire and impacts, the violence of a young system. But around a quiet red dwarf, life could begin in profound peace. The glow is faint, but for a planet like K2-18b, it is enough. Enough warmth for oceans, enough light for chemistry, enough time for everything. Perhaps that is the universe's quiet truth, that life does not crave brilliance, only balance. That it can bloom under crimson skies as easily as under blue. That existence itself is adaptable, universal, patient. So when we look toward Leo and see that faint red spark, we are not seeing emptiness. We are seeing endurance. A sun that has been burning softly for billions of years and will burn for trillions more. And beneath its calm glow, behind curtains of hydrogen and mist, a living world may still be turning slowly, silently, in the light of an immortal star. The light from K2-18b's red sun filters through layers of hydrogen and vapor before it finally reaches the oceans below. To the human eye, those skies would not be blue, but a pale amber, shading to deep rose near the horizon. Clouds drift slowly, broad and dense, tinted by the faint copper glow of the star. The air itself would shimmer, heavy, rich, almost luminous, a living lens of gas that both shields and sustains what lies beneath. This atmosphere is the planet's great architect. It is not thin and fragile like Earth's, but vast and thick, hundreds of kilometers deep. Hydrogen dominates, laced with carbon dioxide, methane, and water vapor. Together, they create a powerful greenhouse, yet not a destructive one. Instead of scorching the surface, the heat spreads evenly, keeping the world in perfect thermal equilibrium. Water neither freezes nor boils. It simply endures, flowing through endless cycles of vapor and rain. From orbit, the upper layers appear remarkably calm, but deeper down, the air grows dense enough to blur the very line between sky and sea. The clouds merge with mist. Mist dissolves into ocean. The boundary of air and water is not a sharp surface, but a gradient, a slow, gentle fading of one into the other. Beneath that soft veil, sunlight weakens, replaced by a crimson glow that seeps through like light passing through stained glass. The ocean itself may be hundreds of kilometers deep, far beyond any pressure our submersibles could ever hope to survive. Hydrogen mixes freely with water, creating a liquid unlike any found on Earth. It would be lighter, more compressible, able to remain fluid across an enormous range of temperatures. It is a sea where chemistry reigns supreme. A cradle of molecules that might assemble, divide, and breathe. If life exists there, it likely began in those immense depths, far from the reach of light. On Earth, we once thought sunlight was absolutely essential to creation. But at the bottom of our own oceans, near volcanic vents, we found entire ecosystems that thrive in complete darkness, powered not by light, but by chemistry. They live on heat and minerals, on gradients of energy rather than rays from the sun. The very same could be true on K2-18b. Its oceans may harbor vast hydrothermal fields where hydrogen and carbon mingle, giving rise to the first spark of biology. The pressures down there would crush steel. Yet for living cells, pressure can be a form of protection. It stabilizes fragile molecules, drives crucial reactions, and keeps water liquid even when the temperature soars. If microbes ever took hold in those depths, evolution would have had billions of calm, stable years to perfect them. Webb's instruments can't see that far below the clouds. But the atmosphere above profoundly betrays what happens beneath. The gases we detect, methane, carbon dioxide, traces of dimethyl sulfide, all strongly suggest an active cycle connecting sea and sky. On Earth, that delicate balance is maintained by life. Algae producing methane, microbes consuming it, plants exhaling oxygen. On K2-18b, something strikingly similar could be at work, though shaped by very different rules. The absence of ammonia is another compelling clue. On dead planets, ammonia tends to build up over time, a leftover of chemical decay. But here, it's missing, likely converted into more complex compounds or broken apart by living metabolism. Even without seeing a single organism, the atmosphere behaves as if it is being constantly adjusted, tuned, and renewed by an unseen hand. Imagine standing, or perhaps floating, somewhere within that environment. The air would be dense enough to feel almost like water around you. Sound would travel slowly but clearly, vibrations passing through the fluid medium in deep, resonant waves. A single drop of the ocean would contain more pressure than the deepest point of the Mariana Trench. Yet to native life, it would feel perfectly natural, balanced, serene. Light would fade quickly with depth. A few hundred meters down, the world would turn red-black, illuminated only by faint chemical luminescence, life's own answer to darkness. Perhaps tiny organisms drift there, glowing softly, exchanging heat and light as a form of language. Perhaps immense, slow creatures glide through the warm abyss, sensing one another through electric fields and pressure waves. Every breath of that ocean would be chemistry in motion. Methane rising from the depths would mix with carbon dioxide from above, producing new compounds that feed microscopic life. Hydrogen dissolved in the water would serve as both shield and fuel. On Earth, such chemistry builds cells. Here, it might build something far stranger, biology that doesn't rely on oxygen at all. And yet, in many ways, it would still feel familiar. Wherever we find life, we find balance. Energy flowing in cycles, waste becoming food, stability maintained through constant change. That is exactly what Webb has seen in the ratios of gases high above the planet's clouds. A living system regulating itself. In the mid-layers of the atmosphere, temperatures and pressures resemble those near Earth's surface. If any part of K2-18b could host organisms similar to ours, it would be there, suspended in the air like plankton in an invisible sea. Tiny microbial colonies might drift with the currents, feeding on trace chemicals, absorbing faint light from the red sun. Each one would be a speck of life carried by the winds, rising and falling through a planet-wide ocean of air. We already know such worlds can exist. In the clouds of Venus, scientists have found patterns of chemistry that hint at microbes floating high above the scorching surface. K2-18b's atmosphere is far gentler. No acid storms, no suffocating heat, making it an even better candidate for aerial life. If the oceans below are the planet's heart, its atmosphere is the breath. Every molecule of methane or dimethyl sulfide that escapes the sea becomes a message, drifting up into starlight. Those molecules crossed space and touched Webb's mirrors, carrying with them the unmistakable rhythm of metabolism, the very pulse of an alien biosphere. The profound beauty of this discovery is that we can read that message without ever leaving home. We can sit on a quiet world orbiting our own star and, through light alone, reconstruct another world's climate, chemistry, and perhaps its biology. From the tiniest distortions in a beam of infrared, we can tell whether another ocean ripples, whether another sky holds rain. And rain it surely does. Water vapor in K2-18b's atmosphere forms massive clouds that rise and fall in slow convection. As they cool, they release showers that fall not as distinct drops but as thick sheets of mist, gliding through the dense air until they vanish into deeper layers. There, the pressure is so high that the rain may turn to liquid metal or crystalline ice before sinking into the ocean below. Every stage of water, vapor, liquid, and solid, could exist simultaneously, stacked in layers like pages of a cosmic story. That cycle, evaporation, condensation, rainfall, is the same one that shaped Earth's weather and nourished its life. It's a powerful reminder that even across light years, the language of nature is universal. Chemistry follows the same grammar everywhere. The deeper scientists look, the clearer it becomes that K2-18b is not just habitable in theory, but dynamic in practice. The planet breathes. It recycles. It changes. Each new observation reveals motion, feedback, adaptation, the undeniable hallmarks of a living system. Somewhere below the clouds, in the pressurized warmth of those alien seas, evolution may have already taken remarkable forms. Simple cells could have merged into colonies. Colonies could have learned to sense, to move, to think. All at a pace measured not in millions of years, but in billions. The red dwarf's slow, steady heartbeat allows evolution to unfold without interruption. We will likely never see them directly. Not yet. But the air they exhale, the molecules they release, have already reached us. Tiny, faint signatures of existence carried across space. They are proof that we're no longer just observers of the cosmos, but participants in its oldest conversation, the profound exchange between light and life. As the James Webb Telescope continues to gaze at this world, every photon it captures brings us closer to understanding the unseen. The next step will be to map the layers of that atmosphere in even finer detail. To measure how the light shifts, how the winds move, how the chemistry evolves from year to year. For now, though, it is enough to know this. Somewhere beneath a crimson sun, beneath clouds that shimmer like silk and oceans that never end, there is balance. A living equilibrium between heat and cold, air and sea, star and planet. It is a balance so perfect it almost feels intentional, not designed, but inevitable, as though the universe itself seeks life wherever it can. And on K2-18b, it may have found one of its most enduring homes. A world breathing softly in the light of a red star, a world whose oceans remember the first warmth of creation, and whose sky carries the quiet, steady pulse of life. For centuries, humanity has looked up at the stars and seen only silence. And then came K2-18b. Not the twin of Earth we expected, but something far more mysterious. An ocean world shrouded in hydrogen, orbiting a red sun, far from anything we've ever called home. Its discovery didn't just expand astronomy. It expanded imagination itself. Because for the first time in history, we're not just wondering if life exists elsewhere. We are seeing the signs that it does. When Webb's golden mirrors revealed the faint traces of dimethyl sulfide, it was more than just data. It was a tremor in the human story. In a few lines of spectrum, the silence of the universe cracked open. Not with sound, but with undeniable evidence. That single molecule bridged a chasm between worlds. It said quietly, but unmistakably, "You are not alone." The meaning of that cannot be measured in percentages or confidence levels. It reaches deeper than science, into philosophy, art, belief, and identity. It forces us to see life not as an exception, but as a principle. For generations, we thought existence was rare, that biology was a cosmic accident born of perfect conditions. But Earth has never been the only stage where the intricate laws of chemistry play out. They've been performing across the galaxy for billions of years, everywhere matter finds the balance between energy and order. We have already seen the hints on our own planet. Microbes thriving in nuclear waste. Bacteria sleeping for millennia beneath Antarctic ice. Creatures living kilometers under the ocean, feeding not on sunlight but on the heat of the Earth itself. Life, it seems, does not wait for comfort. It thrives in defiance of it. And now, 120 light-years away, a world breathes under a red sun, proof that existence is not fragile. If K2-18b hosts life, it reshapes everything. Because red dwarfs, like its parent star, are the most common suns in the Milky Way. For every star like our sun, there are 1,000 like it. Smaller, older, steadier. If even a fraction of them hold planets like K2-18b, then the galaxy is not silent. It is teeming. Billions of worlds, billions of beginnings. The implications stretch far beyond astronomy. They reach into the very equation that tries to measure our cosmic solitude, the Drake equation. For decades, it was a thought experiment, a fragile attempt to guess how many civilizations might exist. Now, one of its most uncertain variables, the likelihood of life emerging, has shifted from a question mark to a near certainty. Life, it seems, doesn't wait for Earth-like conditions. It emerges wherever chemistry and time are given room to work. If biology can breathe hydrogen, if oceans can live beneath red suns, then the definition of habitable becomes almost universal. It changes how we see ourselves. For most of human history, our stories put us at the center, chosen, unique, surrounded by divine emptiness. Then came Copernicus, who moved the earth from the center of creation. Then Darwin, who placed humanity within nature rather than above it. And now Webb, which has moved life itself from the realm of miracle to the rhythm of physics. We are not an exception. We are an expression. One verse in a song that began long before us and will continue long after. And yet, this realization does not diminish us. It connects us. It means that the atoms in our bodies, forged in dying stars, may also breathe and think elsewhere. The same chemistry that flows through our blood may flow through alien oceans. The same physics that ignited our sun lights a trillion others. The James Webb Space Telescope has become our new sense organ. Not eyes or ears, but something deeper. A way to perceive life through light. Each photon it captures is a syllable in the language of existence, traveling for over a century to reach us. And it's not alone in its search. Other observatories, the Nancy Grace Roman Telescope, Ariel, Louvre, and future ground-based giants, are already being built to continue the hunt. Soon, we'll be able to analyze not just one world, but hundreds. If even a handful show the same chemical imbalance, the same whispers of metabolism, then life is not a miracle. It's a pattern. Imagine the night when we realize that every constellation hides a living world. Each faint star, a sun with oceans, clouds, and chemistry of its own. Some of those worlds may be primitive. Others could be ancient beyond comprehension, their civilizations having risen and fallen before the first humans carved stone. But even if we never meet them, their existence changes the meaning of ours. Because for the first time, we know that life on other worlds is much more easily accessible than we thought. For philosophy and faith alike, this discovery reframes everything. If life fills the galaxy, then creation itself is not selective. It is abundant. The sacred becomes not something that happened once in one place, but something that happens everywhere matter organizes itself. The miracle is not that life exists here, but that the universe allows it everywhere. And yet, this revelation carries a mirror. We have found proof that life may thrive under alien skies, while ours, under a bright yellow sun, trembles under the weight of our own making. K2-18b is balanced, steady, enduring. Earth, by comparison, feels restless and fragile. The universe has shown us what sustainability looks like, not as a political ideal, but as a natural law. Perhaps this is the real lesson of K2-18b, that survival is not about domination, but about equilibrium. Life lasts longest, not when it conquers, but when it cooperates. When historians of the future look back, they may call this the moment when astronomy became biology. When we stopped studying light and started studying life through it. Webb's golden mirrors, hanging in the void a million miles away, have become bridges linking our small blue world to something vast and enduring. Because even now, as Webb listens, our own signals are moving outward. Radio waves, television broadcasts, the digital heartbeat of our civilization. They're expanding through space at the speed of light, crossing the distance to K2-18b and beyond. Somewhere, if that world truly breathes, our signals may already have arrived. And perhaps on its crimson shores, something alive has paused, sensing a faint pattern, a rhythm in the static, a sign that it too is not alone. If that moment ever comes, if two worlds separated by 120 light-years recognize each other's presence, it might be the greatest conversation in history. Not in language, not in sound, but in light. Until then, what Webb has shown us is enough. Enough to know that the universe is not silent, but full of hidden songs. Enough to know that life is not fragile but inevitable. Enough to remind us that every molecule of air, every drop of ocean, every breath we take connects us to something older and greater than ourselves. And as Webb continues to gaze into the dark, collecting the faintest whispers of alien seas and skies, we begin to understand the truth that has waited so long for us to hear it. The cosmos is alive. The discovery on K2-18b is not an ending. It's a beginning. The first measured hint that life may not be confined to Earth. From this moment forward, the question changes. We no longer ask if life exists elsewhere, but how many forms it might take and how far it extends. Science is already shifting. For the first time, astronomy, chemistry, and biology are merging into one discipline, a search for patterns that define life across the galaxy. Researchers call it comparative astrobiology. The study of atmospheres, climates, and chemistry as a connected system. No longer isolated dots of light, planets are becoming data points in a living map of the cosmos. On Earth, new laboratories are recreating the conditions of alien worlds. Pressurized chambers mimic the dense hydrogen skies of sub-Neptune planets, testing how carbon, nitrogen, and water behave under temperatures and pressures unknown to Earth. Some experiments run for months, watching molecules evolve into complex organics that may one day help explain how biology begins anywhere. Others focus on the chemistry of disequilibrium, searching for the point where pure physics gives way to metabolism. The goal is to build a library of biosignatures, a catalog of what living atmospheres truly look like, no matter their composition. Artificial intelligence is quietly becoming the interpreter of this new astronomy. Machine learning systems, trained on Webb's data, can recognize molecular patterns invisible to the human eye. Faint combinations of gases, seasonal fluctuations, tiny variations in brightness that might indicate weather or growth. What once took months of manual analysis now happens in minutes. Each new data set refines the algorithms further, teaching machines to detect the smallest chemical heartbeat in the vast noise of space. Around Earth, a new generation of telescopes is preparing to take the next steps. The Nancy Grace Roman Space Telescope, launching later this decade, will identify thousands of exoplanets and provide the first large-scale census of their types and orbits. Europe's Ariel mission will follow, studying the atmospheres of 1,000 of them in detail. On the ground, the extremely large telescope in Chile will combine adaptive optics and massive mirrors to measure the isotopic makeup of distant skies, subtle ratios that can reveal whether a planet's gases come from geology or biology. Together, these observatories will form an interconnected network, a planetary survey system, turning distant points of light into measurable, comparable worlds. The next leap will not be just in data, but in vision. Engineers are developing new optical technologies, coronagraphs and deployable star shades, capable of blocking a star's light so completely that the dim, reflected glow of its planet becomes visible. A single pixel of that light can reveal color, cloud cover, and rotation. With enough pixels, we might one day see continents or oceans glinting under an alien sun. Concepts like NASA's HAB and LUVOIR missions could make that possible within decades. These telescopes would not only detect life's chemistry, but observe its climate in motion, seeing seasons, storms, and the slow rhythm of alien weather. Farther into the future, another vision takes shape. Using the sun itself as a telescope. At a point more than 550 times farther from the sun than Earth, gravity bends light from distant stars into focus, creating what physicists call the solar gravitational lens. A small probe sent there could use this effect to magnify a planet 1 billion times, resolving details as fine as mountain ranges. Reaching that distance would take decades. But the technology is within reach of 21st century engineering. While telescopes study from afar, propulsion research looks ahead to the next frontier, not just seeing other worlds, but reaching them. Concepts like Breakthrough Starshot propose fleets of laser-driven nanocraft traveling at a fifth the speed of light. Their first targets will be nearby stars such as Alpha Centauri. But the same methods could eventually send microprobes to worlds like K2-18b. Closer to home, new propulsion systems, fusion drives, advanced ion engines, solar sails, are being developed and tested in missions across our solar system. Each experiment in deep space navigation, each test of autonomous control, brings the technology of interstellar flight closer to reality. Yet, the future of this discovery is not only about distance. It's also about understanding what it means. As more planets reveal traces of chemistry that suggest life, scientists will begin to study not single examples, but the statistics of existence. What does life prefer? Red stars or yellow ones? Deep oceans or shallow seas? Isolation or complexity? By the middle of this century, the study of life beyond Earth may no longer be a matter of rare finds, but of pattern recognition. Biology seen at a galactic scale. This knowledge will not remain confined to astronomy. The same models used to understand other worlds can help us preserve our own. Studying atmospheric balance elsewhere sharpens our grasp of climate feedback here, how gases stabilize temperature, how oceans regulate heat, how fragile equilibrium can be. In learning how other planets maintain life, we may learn how to keep ours alive. The implications extend further still. If we confirm life beyond Earth, even simple microbial life, it will redefine the ethical landscape of exploration. The Outer Space Treaty of 1967 was written before such discoveries were possible. It governs territory, not biology. New policies will need to protect alien ecosystems from contamination and exploitation, ensuring that contact means cooperation, not consumption. For the first time, space law may have to recognize the rights of life itself, however small or unfamiliar it may be. Beyond law and science, this search will reshape how civilization sees itself. For centuries, humanity has imagined the cosmos as a stage for human progress, a vast emptiness waiting to be explored. But as evidence grows that life exists elsewhere, that narrative changes. The universe becomes not a backdrop but a community. A network of living worlds, each shaped by the same forces that shaped us. Our purpose may shift from conquest to connection, from expansion to preservation. Children born in the coming decades will grow up knowing that the night sky is not silent. Every star they see could host oceans, air, and the slow rhythm of biology. Their maps of the cosmos will not end at the solar system, but extend naturally into the living galaxy. The question that defined generations, are we alone, will fade into history, replaced by a new one: how do we fit within this greater web of life? For now, the work continues quietly. Each new observation adds a line to the story. Each new mission extends our reach. The data will accumulate until patterns appear that no one can deny. And somewhere beyond those numbers, in the faint glow of red stars and distant oceans, we will finally see ourselves, not as observers, but as participants in the same universal process. K2-18b was the first to whisper. Others will follow. Each will remind us that life is not a singular miracle, but a recurring theme in the language of the cosmos. The telescopes we build next will not just look deeper. They will listen better, tuned to the faint harmonies of living chemistry across space and time. The future of discovery will not be measured in miles or even in light years, but in understanding, in how deeply we grasp the continuity between Earth and everything beyond it. And when the next signal comes, when another world joins the growing list of the living, we will recognize it instantly because we will have learned to read the signs, not as distant wonders, but as reflections of a shared origin. The search will never truly end. Each answer will open another horizon, each discovery another question. But this is what exploration means, not reaching the end of the unknown, but continually expanding what it includes. And in that expansion, we begin to glimpse the real future, a civilization that sees itself not as the center of the universe, but as part of its living edge. In the end, discovery often feels less like revelation and more like recognition. A distant echo of something we already knew. For centuries, we looked into the night sky and wondered who might be out there. Now we look and realize they were always there. We just hadn't learned how to listen. The light from K2-18b began its journey before any of us were born. It crossed the gulf of interstellar space while humanity was still learning to leave the ground, carrying within it the faint trace of air, water, and breath. When it finally reached us, it changed what it means to be human. We once believed the universe was silent and empty, an expanse to be conquered or explained. But Webb showed us that silence can be deceptive. The universe is not mute. It speaks in chemistry, in the shifting ratios of gas and light, in patterns that whisper of balance and renewal. Life, it turns out, is not an anomaly. It is a natural way for the cosmos to know itself. That realization reshapes everything. It tells us that the boundary between us and them, between Earth and elsewhere, is thinner than we imagined. The same processes that gave rise to plankton in our oceans may be at work beneath a red sun in Leo. The same laws that shape the air we breathe shape the clouds above alien seas. For the first time, our technology has reached a kind of empathy, an ability to sense the existence of something living without ever touching it. We are learning to understand life not by seeing it move or grow, but by hearing its rhythm in the light of distant stars. There will be more discoveries, more signals, some clear, some uncertain. Each will remind us that we are part of a much wider story. A story not of isolation, but of connection. And each time a new world reveals its chemistry, it will feel a little less foreign and a little more like home. One day, centuries from now, explorers will stand on the shores of other worlds. They will see skies colored by unfamiliar suns, oceans that never knew our moon, mountains that rose without our gravity. But in those landscapes, they will find something familiar. The unmistakable logic of life adapting to survive. And when they look back toward the faint blue point of Earth, they will understand what Webb began. That the search for life was never about finding others. It was about understanding ourselves. Because in every spectrum, every equation, every photon that crosses the void, there is a shared truth. Life is not fragile. It is persistent. It is creative. It is the universe's most eloquent form of continuity. The first breath on K2-18b, the first molecule that learned to replicate under a red sun, may have been the echo of the same principle that shaped us. Different chemistry, same idea, survival, adaptation, awareness. When that light reached Webb's golden mirrors, it completed a circle billions of years in the making. The cosmos observing itself through the eyes of one of its creations. That is what makes this moment more than discovery. It is a reunion. The stars are no longer distant. They are familiar. Not because we have gone to them, but because we now know they live. And so the search will continue. Not driven by loneliness, but by kinship. Every telescope, every mission, every experiment will add another note to the same quiet melody that connects all living things. The universe was never empty. It was waiting. Waiting for something that could see and wonder and finally understand. It was waiting for a number, the 99.7%.